Let's say we have two vectors. A vector v and a vector u. Then between them, those vectors form some angle, and the angle is related to the dot product. U dot v is the norm of u times the norm of v times the cosine of theta. The proof of this is not, to my mind, terribly interesting. We can get it using the law of cosines. Let's turn this diagram into a triangle. Here's the norm of v. Here's the norm of u. Here's the norm of u minus v, because this side of a triangle is the distance between u and v. And the law of cosine says that u minus v squared equals the norm of u squared plus this squared minus 2 times this product times the cosine of theta. So let's get this by itself, because it's supposed to equal u dot v. We're just moving things around algebraically here. So this is 1/2 the norm of u squared plus the norm of v squared minus the norm of u minus v squared. And the key observation here is that because a norm is a square root of a dot product, these norms, when you square them, are going to simplify. The square will remove the square root and just leave you with the dot products. To actually compute these dot products, let's call this v, v1, v2, and this u, u1, u2. So that's 1/2 u1 squared minus, okay, so this will be U1 minus V1, U2 minus V2. That is to say, the first component of this subtraction is U1 minus V1, and it's being squared by the dot product, just like these other first components are. And the second component is U2 minus V2, and it's being squared just like all of the other second components are by this dot product. And almost everything here is going to cancel. In particular, so let's leave these alone just for the moment. When we FOIL this out, we get that. And when we FOIL this out, we get to that. And the only terms that survive are these. This 1/2 kills the 2, and we're left with U1 V1 plus U2 V2, which is indeed the dot product of U and V. So in R2, this is a theorem. You can prove that this is true. And in fact, we just did it. Likewise, in R3, you can prove this geometrically. In higher dimensional spaces, we can use this equation to define the cosine. The cosine of theta, just theta, equals the arc cosine of U dot to V divided by the product of the norms. Using the arc cosine, incidentally, ensures that when you compute the angles, you're getting this instead of that. The arc cosine is restricted between 0 and 180 degrees, so it will give you the smaller angle.